All right, hello everyone. This is Professor Oaks, and in this video, we are going to talk about the Taylor and Maclaurin series. So you can see here what the note says. In the previous times we've talked about series, we've started with a power series and obtained a function. And now we are going to try to start with a function and try to find a power series that represents it. Okay, so that's a general concept here. So let the function f be infinitely differentiable. So that means that we can find the derivatives over and over and over again on an open interval j, meaning that f has the derivatives fn of all orders n greater than or equal to 1 of j, and let a be a number in j, then the Taylor series of the function f at a, right, this is the a, the number in the interval j, that's this power series here. Sum k equals 0 to infinity of ck, and then x minus a to the k, and then that's equal to the series sum k equals 0 to infinity of the kth derivative evaluated at a over k factorial times x minus a to the k. So then the nth Taylor polynomial for f at a is the nth partial sum of the Taylor series. And so that's Pn of x. So P for polynomial, all right, is the sum k equals 0 to n. So instead of going from 0 to infinity, we're going to n of the kth derivative evaluated at a over k factorial times x minus a to k. And if a is equal to 0, then the Taylor series for f at 0 is actually called the Maclaurin series. All right, so again, let me just make sure that you're all clear on a couple of things, just so that you're all aware of what's going on here. All right, so this right here is exactly like what we would have had before. This is just a power series that is centered at a, and then if you compare this to this, then this is the same thing, but this is now what we're saying is the ck. All right, so just try to remember that this is from 0 to infinity. So this is a Taylor series. So a Taylor series is the series all the way from 0, all the terms 0 to infinity. And then here is the same thing. All right, this is just here, though, the Taylor polynomial. And Taylor polynomials are just the sums from k equals 0 to n instead of 0 to infinity. So these go from 0 to n. Now, if you substitute the a equals 0 in here and here into the Taylor polynomial here, all right, then you would get the Maclaurin, all right, the Maclaurin series, or you could have a Maclaurin polynomial. Okay, so that would be sum k equals 0 to infinity, and then f the kth derivative. All right, so the kth derivative of f at 0 over k factorial times x minus 0 to the k, and so that will be equal sum k equals 0 to infinity of the kth derivative of f at 0 over k factorial times x to the k. So this is definitely still a series or a power series, and this is the ck here. All right, so just try to remember that we're not doing anything unusual here. We're just going ahead and just saying these are special series. All right, so some common Maclaurin series, when the a is 0 in the Taylor series, are e to the x. So that's the sum, k equals 0 to infinity, of 1 over k factorial x to the k. So then what will that end up being? Well, that will be 1 plus x squared over 2 factorial plus x to the third over 3 factorial plus x to the fourth over 4 factorial, and so on. So you could prove this, but we are just writing this one out since it is a common one. All right. So then the sine of x is the sum, k equals 0 to infinity, of negative 1 to the k, x to the 2k plus 1 over 2k plus 1 factorial. Again, you could expand this out to prove that it is what I am about to say, but it's just that this is one of the common series. So this is x minus x to the third over 3 factorial plus x to the fifth over 5 factorial minus x to the seventh over 7 factorial plus x to the ninth over 9 factorial, and the minus, and so on. And then the next one that is a common Maclaurin series is cosine of x. So that's sum, k equals 0 to infinity, of negative 1 to the k, x to the 2k over 2k factorial. So this will end up being, well, 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial minus x to the 6 over 6 factorial plus x to the eighth over 8 factorial, and a minus, and so on. All right. So you can see that these two series actually have some sort of relation between them, and we will talk about that in a little while. But let me give you a couple of other common series here, common Maclaurin series. So here is another one. Natural log of 1 plus x, that will be sum, k equals 0 to infinity, negative 1 to the k, x to the k plus 1, all over k plus 1. So that will be x minus x squared over 2 plus x to the third over 3 minus x to the 4 over 4, and so on. And then we have the tangent inverse of x, and this one actually has a special name. This one is going to be called Gregory's series. All right, so this is the sum, k equals 0 to infinity, of negative 1 to the k, x to the 2k plus 1 over 2k plus 1. So this will be x minus x to the third over 3 plus x to the fifth over 5 minus x to the 7 over 7 plus x to the 9 over 9, and then minus, and so on. So these are some common Maclaurin series to memorize for the rest of your life. All right, so now, in addition to all of this, let's suppose that there exists a positive number r and a positive constant m, such that the absolute value of the nth derivative of f at x is less than or equal to m. So this holds for all values of x in the interval from a minus r to a plus r, and all positive integers n. Then f can be expanded into a Taylor series. However, the Taylor series for f doesn't necessarily converge to f. So let's take some examples of this right now, of just finding some Taylor series. All right, so find the Taylor series for f of x equals sine of x at a equals pi over 6. So this should not be that difficult for us to figure out what to do. So remember that a Taylor series is of the form sum k equals 0 to infinity of the kth derivative of f evaluated at a over k factorial times x minus a to the k. So in this case, the a was pi over 6. So we have sum k equals 0 to infinity of the kth derivative evaluated at pi over 6 all over k factorial times x minus pi over 6 to the k power. So this is exactly like what we have been doing before, but now this right here is our ck value, all right? So this is actually just something where we are going to just write out the terms, and then that will be it, all right? So what we need is all of the derivatives evaluated at pi over 6. So f of x was sine of x. So let's go 4 or 5 derivatives out just so that we have enough to sort of like show what the expansion will look like. All right, so the first derivative will be cosine of x. Second derivative will be negative sine of x. And the third derivative will be negative cosine of x. And the fourth derivative will be sine of x, and then you can see that these derivatives start repeating themselves. So I'm just going to stop here since we could do this forever, all the way to infinity, all right? So then we need to evaluate all these derivatives at pi over 6. So f of pi over 6 will be the sine of pi over 6, which is going to be 1 half. Then f prime of pi over 6 will be the cosine of pi over 6, which is going to be square root of 3 over 2. Then we have f double prime of pi over 6. This is going to be negative a half. Then f triple prime of pi over 6 is going to be negative square root of 3 over 2. And then the fourth derivative of f at pi over 6 will be 1 half. And again, you can keep on going from there. All right, so the Taylor series expansion then for sine of x at a is pi over 6 is going to be, so here it is. All right, we'll follow the formula. So it will be f of pi over 6 over 0 factorial, then x minus pi over 6 to the 0, plus f prime of pi over 6 over 1 factorial, x minus pi over 6 to the first, plus f double prime of pi over 6 over 2 factorial, x minus pi over 6 squared, and then, well, keep on going. Oh, we'll do one more. So f triple prime of pi over 6 over 3 factorial, x minus pi over 6 to the third, and so on. All right. So now let's simplify this. So what do we have? Well, f of pi over 6 was a half. So a half over 0 factorial of 1. So then x minus pi over 6 to the 0, which is 1. And then we have here, what do we have? We have, actually, that's just 1, but f prime of pi over 6, so that's square root of 3 over 2 over 1 factorial 1, so x minus pi over 6. And then plus f double prime of pi over 6 over 2 factorial, so minus a half over 2 times x minus pi over 6 squared. And then f triple prime at pi over 6 over 3 factorial will be negative square root of 3 over 2 over 3 factorial happens to be 6 times x minus pi over 6 to the third, and so on. So then if you keep on going here, then what do you have here? Well, I feel like, of course, you could keep on going as far as you would like, right? So let's just do a little bit more cleaning up of all of this. All right. So if I go ahead and clean this up a little bit more, then we have a half times x minus pi over 6 plus square root of 3 over 2 x pi minus pi over 6 to 0, x minus pi over 6, and then that will be minus a fourth, x minus pi over 6 squared, and then minus square root of 3 over 12, x minus pi over 6 to the third, and so on. So could you keep on going on after this? Probably. So let's try to maybe do one more step, and then we will be done with this one here. So here we go. All right, so then remember this is just 1, so we have a half and then plus root 3 over 2, x minus pi over 6, then minus a fourth, x minus pi over 6 squared, minus, and this will be root 3 over 12, x minus pi over 6 to the third, and so on. All right, so that's it. Like, I probably should have just written that as a 1 before, but I'll leave it like this for now. All right, what a time to be alive. Let's try another example here. So let's find the Taylor series for cosine of x at a equals pi over 6. So remember earlier I said that there was a relationship between the Maclaurin series for sine of x and cosine of x. So here we go. So since the derivative with respect to x of sine of x is equal to cosine of x, then that means that this series, the one that we're looking for, the series can be found by differentiating the differentiating, so by, yeah, so the differentiation of the series for a sine of x at a equals pi over 6. So remember, that series was actually, all right, so that series was for sine of x at pi over 6, it was sum k equals 0 to infinity of the kth derivative at pi over 6 over k factorial, and then x minus pi over 6 to the k power. So then, if you remember what is going on here, then this was equal to what we just had. All right, so that would be 1 half, and then plus root 3 over 2, x minus pi over 6, then minus a fourth, x minus pi over 6 squared, minus square root of 3 over 12, x minus pi over 6 to the third, and so on. So that means that the series for the cosine of x at pi over 6, well, that will be derivative of a half is 0. Then we have square root of 3 over 2 times the derivative of x minus pi over 6. So that's 1 minus a fourth times, let's use the power rule. So 2 times x minus pi over 6 to the first. Then minus square root of 3 over 12 times 3 times x minus pi over 6 squared times the derivative of x minus pi over 6, so that's just 1 again. So there we go, and so on. So if I go ahead and I simplify this, I have square root of 3 over 2 minus 1 half, because 2 over 4 is a half, x minus pi over 6 minus square root of 3 over 4, x minus pi over 6 squared, and so on. So this is the series expansion for cosine of x at a equals pi over 6. What a time to be alive. All right, so now let's go ahead and try this next one. Find a Maclaurin series expansion for f of x equals the hyperbolic cosine of x. All right, so remember that a Maclaurin series is just a Taylor series expansion at a equals 0. So again, what do we have here? Well, it's the sum k equals 0 to infinity of the kth derivative at 0 over k factorial, then x to the k. All right, so this is our ck, and we'll proceed as usual. So now all we need to do is go ahead and find all of the derivatives and move forward from there. So f of x is going to be the hyperbolic cosine of x, and to just make it a little bit easier for me, I'm going to just rewrite this in the form of e to the x plus e to the negative x all over 2. So make sure that you remember to have that memorized for the rest of your life. And then what do we have here? The first derivative then will be, all right, so this will be e to the x minus e to the negative x all over 2. Then we have the second derivative, that will be e to the x, then plus e to the negative x all over 2. Then we have the third derivative, so the third derivative, that will be e to the x minus e to the negative x over 2. And then just like before, why don't we go to 4 derivatives just because we can here. So the fourth derivative of x is e to the x plus e to the negative x all over 2. And now we need to evaluate all of these derivatives at 0. So why don't we go ahead and do this? So we need f of 0, so e to 0 plus e to the negative 0 over 2. That will be 1. Then similarly, f prime of 0 is 0, f double prime of 0 is 1, f triple prime of 0 is 0, f fourth derivative at 0 is 1, and so on. So you can see these actually would just alternate 1, 0, 1, 0, 1, 0, 1, 0, and so on. So then if I go ahead and I write out this series expansion, so we'll start with k equals 0 here. So let me get a different color pen just to make this a little bit more distinct from what I just wrote here. So we have the f of 0, so that was 1 over 0 factorial x to the 0 plus, all right, 0 over 1 factorial x to the 1 plus the 1 over 2 factorial x to the 2 plus 0 over 3 factorial x to the third, and then plus 1 over 4 factorial x to the fourth, and so on. All right, so now if I go ahead and look here, I can see that all of the odd power terms actually are zeroed out here. So I'm left with just a simple, well, what will this end up looking like? Well, this is 1 plus x squared over 2 factorial, and then plus x to the fourth over 4 factorial, plus x to the 6 over 6 factorial, and so on. And this particular one, unlike the last one up here, that may have been a little bit harder to do this for, I could just rewrite this fairly easily in a, well, actually, the last one wouldn't have been that hard to do. I just would have had to go back and and look at look at what I had originally for the sine of x, and then and go from cosine of x back to sine of x. But anyway, I can rewrite this as just sum k equals 0 to infinity of x to 2k over 2k factorial. So what a time to be alive. I really hope that you enjoyed this example, because we're going to do another one here. So let's go ahead and find the Maclaurin series expansion for f of x equals natural log of 1 plus x over 1 minus x. All right, so now let's go ahead and remember that we have the Maclaurin series means a Taylor series expansion at a equals 0. All right, so really it's the same procedure, but a is just automatically going to be 0. So, well, one way that we could do this is by using the log rules. All right, so by the way, like there's a lot of things that you could actually do here, but one of them is to just look at the log rules and rewrite this f of x as natural log of 1 plus x minus natural log of 1 minus x. And then we are going to use the known Maclaurin series. So the known Maclaurin series will help us so that we don't have to just find all of the derivatives from scratch ourselves, all right? So the natural log of 1 plus x is the sum k equals 0 to infinity of negative 1 to the k, x to the k plus 1 over k plus 1. So this is x minus x squared over 2 plus x to the third over 3 minus x to the fourth over 4, and so on. And so now if we want the natural log of 1 minus x, then this will be the same series here, but instead we need to look at this and compare them and see that this was plus x, and so this one will be minus x. All right, so what we're going to have here is negative 1 to the k, and then negative x to the k plus 1, and then all over k plus 1. So then all we have then is negative x minus negative x squared over 2, then plus negative x cubed over 3, then minus negative x to the fourth over 4, and so on. So let's simplify this here. So negative x and then minus negative x squared over 2, that's minus x squared over 2, then plus a negative x cubed over 3 is negative x cubed over 3. And then we have a negative x to the fourth, so negative x to the fourth over 4. And so you see that all of these are going to end up being negative. Which, again, you could have actually looked at this right here, right? And you could have rewritten this as negative 1 to the k, and then negative 1 to the k plus 1, and then a negative x to the, well, a positive x then. So a positive x to the k plus 1, and then this would be a negative 1 to the 2k plus 1. And so that means that this exponent on the the uh, negative 1 is always odd, which means that all of these would end up being negative here. All right, so just try to remember that that is what's going on here. All right, just try to remember that's why these all end up being negative here. So now we'll substitute these two series in. So this was natural log of 1 plus x, and then this other one right here was the natural log of 1 minus x. So what do we have when we substitute those in? We have that this is equal to x minus x squared over 2 plus x cubed over 3 minus x to the fourth over 4. And then we have minus a negative x minus x squared over 2 minus x cubed over 3 minus x to the fourth over 4 minus, and so on. So now what I need to do is I should go ahead and just think about this, like just distribute all of these negatives. So that actually means that these all become positive here. So x minus x squared over 2 plus x cubed over 3, then minus x to the fourth over 4 plus x squared over 2, then plus x to the third over 3 plus x to the fourth over 4. All right, so this and then plus this. All right, so do any of the terms actually zero out here? Well, all right, the x squared over 2 zeros out, and then we have an x to the fourth over 4 zeros out. So all of the even power terms zero out, but then you can actually see, if you look carefully, that for the odd power terms, they're all going to be double. All right, so we have two of all of them. So what we have is actually 2 times x plus x to the third over 3 plus x to the fifth over 3, or 5, and so on, right? So now I can actually rewrite this as just the sum k equals 0 to infinity of 2 times x to the 2k plus 1 over 2k plus 1. So there you go. That's how I would write the Maclaurin series for f of x equals natural log of 1 plus x over 1 minus x. So let's try another exciting example right now. So let's find the Maclaurin series expansion. Again, that means the Taylor series expansion at the a equals 0, for f of x is x e to the negative 3x. All right, so we're going to again use a known Maclaurin series. So let's use the known Maclaurin series, and then, well, all right, I don't have a Maclaurin series that looks exactly like this, but I do know that e to the x is equal to sum k equals 0 to infinity of x to the k over k factorial, which is 1 plus x squared over 2 factorial plus x to the third over 3 factorial plus x to the fourth over 4 factorial plus x to the fifth over 5 factorial, and so on. So then if I want e to the negative 3x, then I would actually have, all right, so what will this end up being? Well, that will be, here we go. So it's 1 plus, now try to see how this is going. Right here, the x was in the exponent, right? So whatever the exponent is will be all of these x's right here. So this will be 1 plus negative 3x, then plus negative 3x squared over 2 factorial, plus negative 3x cubed over 3 factorial, plus negative 3x to the fourth over 4 factorial, plus negative 3x to the fifth over 5 factorial, and so on. But then, if I want to have x e to the negative 3x, I need to actually go ahead then and multiply this series by x. So x, 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 and then all of the terms after that by x as well. All right, so now if I go ahead and I simplify this a little bit here, 1 times x is x, then x times negative 3x is negative 3x squared, and then I'll follow that up by 9x cubed over 2 factorial, then minus 27x to the fourth over 3 factorial, plus 81x to the fifth over 4 factorial, and then a minus, and so on. All right, so I hope that you're enjoying this, because now I'm going to write down what the series looks like in a closed form here. So it's a sum, k equals 0 to infinity. All right, of what will this end up being? Well, it's negative 3 to the k, x to the k plus 1 over k factorial. So this here, right here, is the Maclaurin, Maclaurin series for f of x equals x e to the negative 3x. All right, what a time to be alive. I really hope that you enjoyed finding these Taylor and Maclaurin series expansions. So now let's go ahead and look at the errors here. So let's look at an example here. All right, so recall that the absolute value of the error does not exceed the absolute value of the first neglected term. So in general, we're going to use this rule that the absolute value of the sum minus the nth partial sum is less than or equal to the first neglected term, and that should be less than 5 over 10 to the n plus 1 power. So let's use the power series to estimate the numerical value of each expression with an error not exceeding 5 over 10 to the 5. So that means that this means that, well, what do we want to do here? Well, here we go. All right. So if this is a 5 over 10 to the n plus 1, and this is 5 over 10 to the fifth, then that means 5 is equal to n plus 1, and so we need n equal 4 terms. All right, so here's what we have. We have sine of x is equal to x minus x to the third over 3 factorial plus x to the fifth over 5 factorial minus x to the seventh over 7 factorial, and so on. So if we want to estimate the numerical value of sine of 0.1, well, here it is. Sine of the 0.1 is 0.1 minus 0.1 to the third over 3 factorial plus 0.1 to the fifth over 5 factorial minus 0.1 to the seventh over 7 factorial, and so on. All right, so I hope that you are enjoying this. So now if we want the approximation, all right, so let's go ahead and see what we, if we actually need all 4 terms that we had here. All right, so then we know that this one right here is going to be, that's 0.000167, and this one is going to be 0.000000, so that will be 833, and this one right here is going to be, all right, so this one will be 0.000000001984 12698. All right, so there you go. So hopefully you really enjoyed seeing this here. So now if you know that this is supposed to be the error, then you see that this actually is already less than the error right here. This one is not less than 0.00005, but this one is. So actually this is less than the error. So that means that you really only need the first 2 terms. So sine of 0.1 is approximately 0.1 minus 0.000167, and so that will be 0.099833. And if you want the exact value of the sine of 0.1, so here we go. Let's calculate that. And remember, we're doing all of this so that we don't need to use a calculator. But if I needed to use a calculator, then the calculator would give me sine of 0.1. So let's see, what is that going to be? That will be approximately 0.0998334166. So did the approximation here using just two terms get really close? Yes, I think that's as close as you're going to get fairly quickly, right, with just two terms. So now let's try another example. So I hope that you enjoyed that. So this will be our last example here, unfortunately. So I hate to have to leave you so soon, but that is the case. All right, so now there is another example right here. So we have cosine of x in this particular example here. So cosine of x is going to be 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial minus x to the 6 over 6 factorial, and then plus, and then so on. All right. So then I need the cosine of not x, but instead the square root of x. So I'm going to replace the x's with the square root of x's here. So this will be cosine of the square root of x is 1 minus square root of x squared over 2 factorial plus square root of x to the fourth over 4 factorial minus square root of x to the 6 over 6 factorial, and so on. And then I will simplify to get 1 minus x over 2 factorial plus x squared over 4 factorial minus x to the 6 over 6 factorial, and so on. So you don't have to simplify, but it would make it a little bit easier. So remember, this is cosine of the square root of x. But then I actually need it to multiply this by another x right here. So x, 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 and then x times all of the rest of the terms as well. All right, so what do I have once I do that and I simplify all of this? I have x minus x squared over 2 factorial plus x to the third over 4 factorial minus x to the fourth over 6 factorial, and then so on. All right, so like, what do you want to say that we have here? Well, actually, oh, that should be 3, not 6. There we go. What do you want to say that we have? Well, you could keep on going if you wanted to, right? But I'm not going to keep on going any further because I feel like this is good enough for me to tell sort of a pattern of what is going on. And now I know that this is x cosine of the square root of x. And the next thing that I wanted to do was take the integral. So I'm going to take the integral, and just for now, the indefinite integral. All right, the indefinite integral. So the indefinite integral of this dx, indefinite integral dx. So now remember, I can just integrate each individual term. So that would be integral of x cosine of the square root of x dx is 1 minus, all right, 1 x squared over 2. So 1 half x. I, I lost where I was in the problem. So 1 half x squared, and then minus, all right, so we have, well, however you want to write this, but x to the third over 3 times 2 factorial, and then plus x to the fourth over 4 times 4 factorial, and then minus x to the fifth over 5 times 6 factorial, and so on, all right? And then what I need to do is I need to find oh, by the way, this is actually plus c. All right, because I have not actually found the definite integral yet. But then if I want the integral from 0 to 0.25 of x cosine of the square root of x dx, then what will this end up being? Well, this will end up being, well, evaluate this, all right, from 0 to 0.25. So we have 1/2 times 0.25 squared minus 0.25 cubed over 3 times 2 factorial plus 0.25 to the 4th over 4 times 4 factorial minus 0.25 to the 5th over 5 times 6 factorial, and then plus, all right, and so on, but then minus, all right, so the 1/2 times 0 squared minus 0 cubed over 3 times 2 factorial plus 0 to the 4th over 4 times 4 factorial minus 0 to the 5th over 5 times 6 factorial. Those are all actually 0, right? So this here is equal to 0. So that's okay. We can just be okay with the fact that that term actually zeroes out. And then I will just go ahead and look at all of these terms here. So this first term here is actually 0.03125. This next one is 0.002604. And this next one is 0.00004 069, and that is actually less than 0.00005. So we know that that's the term that we can start neglecting at. All right. So that means, therefore, the integral from 0 to 0.25 of x cosine of the square root of x dx is approximately 0.3125 minus 0.002604. So that's about 0.028645. And then if I found the exact value of this integral, all right, so let's go ahead and I'll calculate the exact value for you here. So here we go. So here, let's just calculate the exact value. So where is the integral here? So 0 to the 0.25 of x times the cosine of the square root of x dx. And that will give us about, all right, here it is. All right, so that would be about the 0.0286862532. And then you can see here that even after just 2 terms here, that we still had a fairly good approximation. All right, so there you go. So it only took 2 terms to get a fairly good approximation of this definite integral here using a Taylor series. So that is all I have to talk to you about Taylor and Maclaurin series, and then estimating these errors here. So I really hope that you enjoyed this video and that you're already looking forward to the next one. Thank you and have a great day.